Okay, in today's video, we are going to go over an introduction to the electric field. Now, in this video, we're just going to talk about how to determine the direction and the magnitude, but we're not going to actually calculate any magnitudes. I'm just going to go through the equation, and then in the next video, we'll do a few simple electric field calculations. And I think it's important that you watch this introduction video and the next video on doing the calculations to get a good understanding of how the electric field works. It's a little bit confusing, okay? And I think people have a hard time conceptually because we're going to talk about the electric field and then the force per coulomb on a separate charge. So you need to really watch both videos. Now, in this first video, we're going to tell you that by definition, the electric field is the force per unit of charge. And I think the confusing thing is it's which force on which charge. All right? Now, by definition, not by definition, it is a force, so therefore it's a vector, and therefore it has a magnitude and a direction. Now, the first thing we're going to do is talk about the direction. How do we determine the direction of the electric field around this charge? I also want to say that in order to have an electric field, you only need one charge. Every charge has its own electric field. Now, we can have more than one charge and add up the electric fields, but in order to have an electric field, you only need one charge, which is different than Coulomb's law or the electric force. In order to have a force, you need to have two charges. Okay, so this is where it gets a little confusing. There's a little bit of a difference between, or there's really a big difference between the electric force and Coulomb's law and the electric field, and I hope to straighten that out in this video. But I want to point out that we're going to look at the direction first. Now, how do we figure out the direction of the electric field around this charge? Well, what we do is we take out this very special thing called our test charge. The test charge is a very small positive charge. There are two things you need to remember about the test charge. One is it's very small. It's very small in magnitude compared to the main charge, this capital Q main charge. And therefore, it does not really disrupt the electric field of this main charge in theory. Also, the test charge is always positive. So it's positive and it's very small. And what we do is we ask ourselves, if I put this test charge right here, in which direction is the force going to be on this test charge? Well, this is positive and this is positive, so therefore the direction of the force is like that. So we could represent the electric field with an arrow that points away from the charge. Now let's try another test charge over here. What happens? Well, once again, we still have two positive charges, so the force on the test charge is still going to be away from the main charge. Well, let's just try, because maybe it's different, like way out over here. Well, once again, it's still positive and positive. So the direction of the electric field, the direction of the force on that test charge is away from the main charge. And you can see basically now if we put a test charge anywhere, because it's positive around that positive charge, that the direction of the electric field is away from the main charge. Okay, and that's how we would draw or represent graphically the electric field, those arrows pointing away from the center of our main capital Q charge. Now, one thing I want to say about the magnitude is we can represent kind of in general, okay, qualitatively, the magnitude of the charge by the magnitude of the electric field by the density of the electric field lines. You can see that here, close to the charge, the lines are relatively close together, whereas here, away from the charge, they're farther apart. That means that here, away from the charge, the electric field is weaker than it is here close to the charge, okay? Because the lines are farther apart. Now, if we wanted to show an increase graphically in the electric field, let's say we wanted to show it doubling, then we would just simply draw twice as many lines like that. That represents a doubling of the electric field. Okay, now let's see what it would look like around a negative charge. Now we're going to do the same thing. We're going to take out our test charge. It's still very small and it's still positive. And because it's positive and this charge is negative, the direction of the force on the test charge is going to be toward the main charge. Well, let's try it over here because maybe, again, well, still towards negative and positive. And let's try it really here close, still towards the charge. And therefore, you can see anywhere around a negatively charged particle, the electric field points towards the charge. Positive away, negative towards, or from the positive to the negative. And that's how you determine the direction of the electric field. Okay? Now, what about the magnitude? All right, once again, here is our charge, and we have it represented, the field, by these lines. Now, we said earlier that the definition of the electric field is the electric force per unit of charge, but what force on what charge? And it's not the force on this charge, and it's not the unit of charge of this charge. It's the force on a different charge that is around or is in the electric field from another particle. This is capital Q. I like to call this the main charge. This is lowercase q. It is the one, the secondary charge that is going to field the electric force, the amount of force per unit of its charge. So we have the electric field. E is equal to, by definition, the electric force. So we put the electric force per unit of charge. Now you can see I put lowercase q because it's per unit of this charge, which is placed right here away from this main charge. Okay, you remember the equation for the electric field has this big Q in it, but when we have the definition, or another way to calculate the electric field, is just take the electric force at this point divided by the amount of charge placed at this point away from the main charge. Now that means that, and by definition, the electric field is going to have the units of newtons per coulomb. Newtons of force on this charge per coulomb of this charge. Now, we're going to expand this. E is equal to the electric force. This is the equation K, Q, Q divided by D squared. This is Coulomb's law. That's how we calculate the electric force. But now, in our definition here, it's per unit of this charge. So now I'm going to divide this by this charge. Okay, this charge is this charge. This charge is this charge. Well, we're going to divide it by that same charge. And that's going to allow those two charges to cancel out. We kind of cancel those out. You can see now we're left with our previous equation, which we said is E, the electric field. We calculate the electric field by taking K, multiplying it by the charge of this main charge. And then we pick some distance, like this charge is right here, so that's some distance. And then we divide it by the square of the distance. And then we can say that right here, the electric field strength has some strength, some number of newtons per coulomb. Depending on how much charge we put there, then it will feel a certain number of newtons of force. Okay, so that is how we calculate the electric field using this equation. Now there's one other equation that we kind of use, and you can see if we take this one, E equals the electric force divided by the charge, we can actually figure out the force on the charge. All I did was rearrange this, cross multiply it, I get Fe equals EQ. We can figure out the amount of force on this particle if we know the electric force at this point, if we know the electric field at this point and we know how much charge we put there. Okay, now this comes in handy when we have a whole variety of charges. We can figure out the electric field there, and then we can think about, well, what would the force be, or we can calculate what would the force be based on the charge, and we can switch out different charges and get the electric force pretty easily. Okay, so now I said it's a good idea. That's the end of the introduction. I said it's a good idea if you watch the next video where we do a few simple calculations, and that will be helpful for you, I think, also. Okay, so thank you very much for watching. I hope you found that helpful in figuring out the difference between kind of the electric force and the electric field. If you found that helpful, you can give me a thumbs up or a nice comment in the comment section below, and we will see you in the next video. Thank you for watching.
Electrostatic shielding. Electrostatic shielding is the method of protecting a certain region of space or any sensitive instrument from the influence of the external field produced by an electric charge. Instruments used for measuring high voltage are protected from intense electric field by enclosing them in hollow conductors called Faraday's cages. Faraday's cage. The fact that there is no electric field inside a closed conductor when it contains no charged bodies was demonstrated by Michael Faraday. He made for himself a large wire cage supported on insulators and sat inside with electroscopes, which were electric field detectors. Faraday observed that there was no deflection of leaves of the electroscope placed inside the cage when the cage was charged by an induction machine, and also he could sit comfortably inside the cage. The hollow conductors used to protect any person or instruments from intense electric fields are called Faraday cages.
Electric shielding. For this, I want to start with a few questions. So first of all, what do you remember about like charges? Like charges. With that, you probably remember that like charges repel. And so when we talk about electrons on a negatively charged object, what we can assume is that those negatively charged electrons are going to be repelling each other. Meaning, if we have a conductor that's negatively charged, those electrons are going to be repelling each other. Those electrons are going to be spreading out across that conductor in a way so that they are as far away from each other as possible because they are like charges. Now, if we have a conductor that is an empty shell, which I'll show you in class, what this causes is the electric field inside of that conductor is going to cancel out. And so there is no electric field essentially inside of that conductor. And this is what we call electric shielding. This is what we use to shield electronics from outside electromagnetic radiation. It's what we use for Faraday cages, things like that. And so what happens is the outside of that conductor will have an electric field, but the inside, because of the conductor, it will cancel out. It doesn't matter the shape of the conductor. In fact, depending on the shape, you can have a different concentration of charges, which I'll show you in just a little bit. But with the shape and the concentration, they will still cancel out on the inside, but not necessarily on the outside. If you've ever seen videos of a car being hit by lightning or of an airplane being hit by lightning, the charges typically stay on the outside of the car. So if you are driving and you're going through a lightning storm, you don't want to get out of the car. You want to stay inside of the car because the car essentially is going to be a Faraday cage for you, and it will protect you if you're on the inside. If you're outside of the car, you won't have any shielding, and you could easily get hit by lightning if you were in that situation. If you've ever seen demonstrations with huge Van de Graaff generators, sometimes there's a person that is inside of a cage, and you can actually see this person touching the inside wires of that cage, and it's because the charges distribute on the outside of the cage because of this shielding effect. All right, let me show you a diagram. This is a drawing of the electric field. If we have a charged particle, in this case this is going to be positive because you can see the arrows are going away from it, and also with the concentration of the negative charges, you can see that if we have a conducting sphere and we have a positive charge getting close to it, this will induce the electrons to move more to the right side, and you can see the electric field concentrating there. And because the electrons are going to concentrate over on the right side, the left side is going to be induced to have a positive charge, and so you can see the electric field over there. What you also notice is the inside of this conductor has no electric field, because with the way these electrons are going to be organized on this, the field on the inside essentially cancels out. Okay, so this conductor is oddly shaped and is positively charged, so electrons have been removed from it. And so what do you notice about the concentration of charges? You'll notice that it concentrates towards the peaks, where the radius of curvature is the smallest. Now, what you want to be careful about is when we talk about something that is positively charged, we have not added protons. What we have done is we have removed electrons. So you might be thinking, well, how come we have positive charges that are distributed unevenly? And the way to really think about it is, it's not that the positive charges are distributed unevenly, it's the electrons are distributed unevenly, and we have a net loss of electrons, and so the electrons will redistribute themselves around here in a way so that the positive charges look like this. Now, if we have it as negatively charged, you can see it a little bit more here, and this is going to be all over on the surface. And you can see that the density of the charges go like this. So where the radius of curvature is the smallest, you have the densest charge. Where the radius of curvature is a little bit larger, it's going to be a little bit less dense. And where there's very little radius of curvature, almost straight, it's going to be the least dense in terms of its charge. Now what's going to happen is if we were to draw the electric field inside of this, there would be no electric field. It would all cancel out on the inside. What you can see here is how the field lines would be drawn for something like this. And these are equipotential lines, so the lines are equally separated by their strength. So that is electric shielding. You have a conductor. The outside has an electric field, but the inside, the field has essentially canceled out.